Good afternoon, everybody. Welcome to SADS Facebook Live, episode number 47. Can you guys believe it? It's great to be with you today. I'm Mike Ackerman, genetic cardiologist at Mayo Clinic and director of our Winland Smith Rice Genetic Heart Rhythm Clinic. And on behalf of Alice Laura, you know, she's our CEO of the SADS Foundation, the Sudden Arrhythmia Death Syndrome Foundation. Thanks for choosing to join us today. We've had hundreds of thousands of views in our previous 46 sessions. Last week's was another highlight as we updated you all about the state of COVID-19 pandemic. It did not go away, believe it or not. Even though we have a new president in the United States, the pandemic did not disappear and it still rages. We are approaching 100 million cases worldwide. We'll probably reach that by next week. We're at 97 3/4, over 2.1 million deaths in the United States, 24.6 million cases. So about a quarter of the COVID-19 cases reside here in the United States, and over 411,000 deaths. Good news, as we all know, is we've been vaccinating healthcare professionals and the fragile, the elderly since mid-December. Our program at Mayo Clinic, vaccination program, started on December 17th, my anniversary, and I got mine. I get my second shot on Wednesday. So when it's time for yours, get your vaccine. If you are 16 or older, get the COVID-19 vaccine. Which one? Whichever one is there. Pfizer's, Moderna's, or when the Johnson & Johnson gets approved, that one. So whichever one is in your community and available, and you are 16 or older, get it. Until then, do all the right things. Yes, put on the mask. We don't need a mask mandate. That national mandate, that's ridiculous, but we just need to do it. And look at this. Some of you, in fact, I got to see if you're watching, because I know you watch sometimes. This is the one you just sent me from my alma mater, Luther College. Go Luther College. So thanks for sending that this week. But whatever one you have, the best one to wear is the one that's on your face. So do it. Do your hands. Don't forget that. Stay distance responsibly, but stay connected deeply. We can do this, everyone. Many of you are corona-free still, as am I. And I'm trying to keep myself and my family corona-free for as long as possible, hopefully until they're all vaccinated. So welcome back. And many of you have joined in and are getting a little greeting from all over the world. So Guten Tag for those in Germany, Erica and Katrin, great to see you. And Nanny from the Netherlands. I think we had a huge turnout last week from the Netherlands, and Dana from Ireland. So all of you, welcome. Today's program is different, but really special, and I'm really excited to introduce somebody who's really special to me. We've been connected for a long time in different ways. Dr. Andrew Landstorm from Duke University, and Aaron's going to be bringing on Dr. Landstorm. And Andrew is special. Why? Because he's one of my pupils, and he's one of my absolute best from his time with me here at Mayo Clinic in Rochester, Minnesota, and his years in the Mayo Clinic Alex School of Medicine as an MD student, his years in our Graduate School of Medicine as a PhD student, where he did his doctoral work in my lab under my mentorship, and truly one of my very special mentees that I'd like for you to get to know. Some of you will also get to know him tomorrow, because he's going to be doing the webinar for families with type 2 long QT syndrome. So Aaron, bring on Andrew. And there he is, not a day older than when he was a pupil in my lab.
Oh, Mike, that's very kind of you, although maybe the gray hair might give you some clue. It's wonderful to be here. Thank you.
It's great to have you, Andrew. Will you give a sense for those listening? We have families with all types of genetic heart rhythm diseases that join us. SADS mostly long QT, but the other channelopathies, and you families know if you are Brugada, CPVT, or if you're a cardiomyopathy family, ARVC, or any of the others, Andrew's going to give you a glimpse of his journey from here to there. And then we're going to go into a review of some really exciting advances that occurred in 2020. But before the advances, Andrew, who are you anyway?
Well, thanks, Mike. Well, first off, thank you again for the invitation to be here. This really is a treat. Thank you for everyone for tuning in, and thank you to SADS for the opportunity to be here. So you might remember I'm a North Carolina native. Grew up in Raleigh, North Carolina. Went to school in Chapel Hill, and I know I'm faculty at Duke. And I know occasionally around this time of year there's a sports called basketball that sometimes people disagree with, but I'm a UNC undergrad. I think maybe the basketball team is slightly better, but we'll see. Mm-hmm. And I thought I would stay in North Carolina, but then when Mayo Clinic offered me the chance to go up to Rochester, Minnesota for the MSTP, the Medical Scientist Training Program, I jumped at the chance, mainly because of how phenomenal the program is, and of course the hospital requires no introduction. I've always loved genetics, even as a kid. And it was my time with you, Mike, that really showed me that genetics plays an important role in the care of patients, and what the power of genetics can be to improve lives and to make discoveries. And I learned that right there with you at Mayo Clinic. I then went to Houston, Texas, Texas Children's Hospital, completed a residency in pediatrics and a fellowship in pediatric cardiology. And just because I love school, I went on to do additional fellowships in pediatric electrophysiology and then a postdoc with Xander Warrens in cell physiology and biophysics. And Mike, I attribute this to my time with you as well, because you were the one who paired us up when I was a graduate student. And it was wonderful to continue that research in kind of a different way with Xander. We were all set to stay in Texas for a little bit, had the beginnings of a lab going. And then, as luck would have it, we had the opportunity to come back to North Carolina. And so this has really been a homecoming for us. My wife has just been ecstatic. I've been ecstatic. And this is my third year now at Duke.
Wow.
I spend most of my time in the lab. We have some NIH funding to ask some very basic questions about how mutations can cause disease in cardiomyopathies and in channelopathies, which is really exciting. And the other part of my day, I spend seeing patients and growing a cardiovascular genetics clinic, mainly on the pediatric side, and then collaborating with our adult cardiology colleagues to make sure we can get the whole family seen. So that's what I've been up to these days, and happy to be here.
Well, great. And Andrew, you have done a great job. It's fun to watch the next generation of genetic cardiologists and genetic cardiovascular scientists like you get launched so well and do so well. And I hope that I can invite you back to actually have you share some of your own research and what questions your program and your lab are asking and answering. But today, you're coming with us from a different role that you play, and that's with a journal called Circulation, Genomics, and Precision Medicine. Tell us what you are doing with that journal, and then we're going to jump on in with some real treats for our audience today.
So for the past couple of years, I've really had the pleasure and the privilege of being one of the assistant editors for the journal. Editor-in-chief, has made a priority to sort of incorporate junior faculty members who might be able to play this role. And one of the things that we do, in addition to being able to see some of the top science that gets submitted, is to help sort of engage the community through things like social media. And so really in this role, it's really twofold. One, to kind of be be a guide for some of these incredible studies that have come out, but also to make sure that people know about them and people engage. And so happy to do this. I've got 5 of the best, I think, and happy to discuss.
Great. Well, I tasked Andrew to do something really hard, and that was to go through the year just closed, 2020, look at their journal, Circulation, Genomics, and Precision Medicine, where the chief of the journal is a dear, dear friend of mine, Dr. Christopher Semsarian, who we had on our program. Some of you may remember he had to get up really early that morning to join us. And Andrew has picked five articles. Now, he just didn't pick 5 of the best because I asked him to try to pick 2 from long QT syndrome, 1 from Brugada, 1 from CPVT, and 1 from ARVC. And so in no particular order, I don't think, maybe he has them in terms of his top 5, starting with 5 and ending up with his most favorite, maybe not. But Andrew, pitch the first one to us and tell us what you learned from it, what the world learned from it, and what our SADS families might take away from it.
Sure. So I'll start by saying that some of these, some of the topics didn't have major articles that were published in Circ, Genomic and Precision Medicine. And so I have a couple of extra flavors for you to I think round out the number. But the first one fits squarely into the long QT bucket. It's a wonderful study by Elizabeth Streeton at the University of Maryland School of Medicine entitled Casey and Q1 and Long QT Syndrome and 1 out of 45 Amish, the road from identification to implementation of culturally appropriate precision medicine. And in a nutshell, this is a really cool example of how a genetic study can go from a sort of an observation in a population that's fairly unique to something that is informative biologically, and then goes back to actually help the individuals from whom the discovery was made. And so these researchers identified a variant that's very rare in nomad, in the general population, but in an Amish population is markedly overrepresented, found in 1 out of 45 individuals. It's a missense variant in KCNQ1, of course, which can cause, in the right context, long QT syndrome. And this was really a curiosity they wanted to pursue. And so they started by just a good old-fashioned genotype-phenotype correlation. And they found some interesting things. With this variant, QTCs prolonged about 20 milliseconds overall. They also found that individuals who had this variant among the Amish population had a higher history of things like syncope or fainting than others. They also had a higher incidence of a sudden unexplained death in a first-degree relative than people who did not. And this really got them to thinking, well, maybe in this population, as common as it is, perhaps it could be a long QT-associated gene. And through all the guidelines and all the calls that had been made, it was really unknown. It was labeled a variant of uncertain significance. And they said, well, this is certainly interesting. They took it 2 steps further. They studied it in the lab, and in these Chinese hamster ovary cells that normally don't make much in the way of ion channels, they expressed it. And they found that in that context, this particular missense variant, again found in 1 out of 45 Amish individuals, had a complete loss of function of the channel. They also found that when they started to look a little bit more carefully, that perhaps that there was clinical evidence that some of these individuals in this population might have had straight up long QT syndrome. And so they said, well, gosh, all this is really convincing that this potentially could be a disease allele. And they started to treat the individuals who had long QT syndrome with beta blockers, and actually go back to this community that helped them to make this discovery and facilitate care, which I thought was a great way to take it all the way around again.
That's really interesting, Andrew. So for, most of our families are, under the awareness that to be a long QT syndrome causative mutation, that since long QT syndrome affects maybe 1 out of 2,000 humans, and that many of these families know that their long QT1 mutation is theirs and theirs only, and has never been seen in another family. Whereas somebody else's might be one of the more common LQT1 mutations, maybe seen in 20 families in the universe. But now you're saying that we have an LQT1 variant present in almost 2.5% of this specific Amish community, and yet it's still the self-sufficient cause. So how do we reconcile that from the notion that, before, if we had something present in 1% of whites, we were said, well, that can't be the cause by itself. It might modify and it might tweak and it might nudge things, but it can't be the only reason. Did it convince you that in this particular genetic architecture of this Amish community, that single thing present in 2% of them was the smoking gun all by itself?
Yeah, that's a great point. And I think, like all good science, I think sometimes it generates additional questions, perhaps more so than when it started. I think your point's well taken. I think some interesting things that they found was that, this variant really isn't found, at least in the nomad population, suggesting perhaps that as common as it is in this Amish population may indeed be a bit isolated from the rest of the global sort of gene pool, suggesting that perhaps it could be tolerated in this population and held within this population. But you're right. By no means did they find that everybody who had the mutation had clear-cut long QT syndrome. It was simply on aggregate as a whole, they made this association.
So very fascinating. So like we've talked about, some of you, I think even if I'm looking at those joining us, may know that, I have the founder mutation of LQT1 that came from Finland. This is an example, in a sense, of a founder mutation within the Amish. Your second one, Andrew, you started this off really great. So what's the second one you have for us?
Well, the second one is going from long QT1 to long QT2 for this one. This one may be familiar to you, Mike. I found it a fascinating paper. The promise and potential peril with lumacaftor for the trafficking defective long QT syndrome caused the variants G604S, N633S, and R685P using patient-specific reengineering cardiac myocytes. This is work done by Bailey O'Hare out of your team that I found absolutely fascinating. And
time out there, though. Let me just full disclosure to the SADS community. I don't know any of the 5 papers that Dr. Landstrom's chosen. I specifically told him I don't want to know, and I also told him that he has zero expectation to pick a paper from our team. So with that said, I like it that you like that one, because we really like that one too. But tell them what you learned from that one. But I just want to make everybody aware that just because he's one of my most favorite mentees, Andrew had no obligation to select one from our team.
Absolutely. I still think this is one of the best. So as many may know, cystic fibrosis is an absolutely terrible disease, and the chloride channel that is responsible for causing cystic fibrosis can sometimes have a problem getting to the surface of the cell where it needs to be. And a really game changer drug, lumacaftor, has been shown to rescue this, to make sure it gets to where it needs to go in the cell. And there have been some that postulate that perhaps this could be used for other like diseases where the protein doesn't do what we call traffic to the correct spot in the membrane. Long QT2, some mutations prevent that protein from getting to the membrane. And so, Mike, what your team hypothesized, perhaps in the right situation, that this drug could facilitate trafficking of a defective protein that goes to the membrane and might actually be used as a therapeutic to normalize a defective protein and normalize a QT interval that's abnormal because of it. And so you took 3 variants in this gene, and showed, I think, very, very nicely in non-human or non-cardiac myocyte cells that when you express these 3 long QT genes, as you'd expect, they cause a prolonged action potential. And that it doesn't get to the membrane. It doesn't traffic correctly. And when you expose them to this drug, they do get to the membrane. Taking it one step further, did this in induced pluripotent stem cells. So took these mutations from individuals who were, I think it was skin and blood that you all utilized, converted them to the patient-specific derived induced pluripotent stem cells, and then made cardiac myocytes out of that. And very, very interestingly, 2 variants did exactly what the other cells did. So 2 variants, the protein didn't get to the membrane, caused a long QT. You gave the drug, and it normalized quite remarkably. And then the third one, which I wanted to talk to you about, sometimes the ones that don't behave are the most interesting. There was one variant where that was not the case. And for whatever reason, this particular mutation in this gene was sort of insensitive to lumacaftor. And try as you might, it would not rescue. So I think this is really interesting from a number of perspectives. I think principally that you can potentially use this drug as a therapy is really exciting. And then sometimes these sort of oddballs, well, why did it not work in this one situation? Oftentimes can be a clue that you could that may be very meaningful down the road. And so that's what I took from this, and I found it very exciting.
Well, thanks, Andrew. And as you know, and as our SADS Facebook Live community knows, we had an interview with one of my most favorite individuals and a giant in my life and in our field, Peter Schwartz from Italy. And Dr. Schwartz and his team was actually the first to treat a human with lumacaftor and LQT2 and showed that it could work in the full person called me, the body. And we took that observation and that discovery and said, before this gains a lot of traction, we better do some due diligence, because like you pointed out, Andrew, not all LQT2 causative mutations annoy the channel in the same way. And before we just say, hey, here's the new treatment for all LQT2, which, by the way, Andrew's going to talk about LQT2 with the LQT2 families tomorrow in the webinar. So don't miss that. Join him for that. We thought, what if we have this scenario where in the future we could potentially test the drug in the patient's own cells before giving the patient the drug to know if this is a good idea or not. And in the good idea or not, it was good idea twice, but in the third person and in her heart cells, giving that patient this drug could have turned out to have been a very bad idea, because you might be rescuing a channel that is intrinsically defective once it gets to the membrane. And so you might actually bring out a bigger problem than what you might have started with to begin with. And so we liked it a lot. We were building, obviously, you and I talk about a lot how we sometimes stand on shoulders of giants, and we were just standing on the shoulders of Peter Schwartz saying, let's expand the look of lumacaftor. And I think it gave some important insights and a cautionary tale of not so fast with some of the new therapies that we're exploring. So I'm glad you chose that one. You won't find any challenge in why did that one make the top 5 from me. So let's take your third one.
Sure. So this one I think is a really cool paper on Brugada syndrome. So it's entitled SCN5A mutation type and a genetic risk score associate variably with Brugada syndrome phenotype in SCN5A families. This was a big consortium, as you know, Mike, with I think it was 16 centers headed by Elijah Baer. And Mike, you were one of the 16. And I'd love to get your thoughts on this paper too, but I thought it was just top notch. So, as you know, for probably about 7-8 years, we've had a way of thinking about Brugada syndrome, which has evolved. So evolved from the it's a one gene mutation in SCN5A that explains Brugada syndrome, to, there may be other things that come together, multiple genes that in the right context can also cause Brugada syndrome. And there's been, as you know, a lot of work in identifying SCN5A negative Brugada as potentially people who have multiple genes that are involved. This paper took it one step further and said, well, are these other variants and other genes, which we know are associated with Brugada, does it explain some of the variable ways that people with the same mutation can either have or have not disease? And in a nutshell, if you have 4 of these variants or more out of, I think, 6, then you are more likely to have that SCN5 variant actually express in a Brugada pattern on ECG. If you had less, you may have still had that SCN5A mutation, but not really seen evidence of clinical Brugada syndrome on the ECG. And so a great example of how, a single gene is clearly important, but the rest of the genome is important too, and a glimpse as to why some patients may have a mutation but not have apparent disease, while others may just be the opposite.
Yeah, Andrew, that's, a great one. And that was a project that was spearheaded by a great guy. He's one of my great friends, Elijah Bear. We've had him on SADS Facebook Live. Some of you may remember him from London. And I think, Andrew, give a sense for the families. As we know in Brugada syndrome, some families are well aware that they are negative. And now we're trying to remind people that you and I aren't surprised when they are gene test negative, because 75–80% are gene test negative. But this insight is really built upon work from Connie Bazina, a phenomenal genetic scientist in the Netherlands, where she really found and put together the package of these Brugada influencing variants, but not causative ones, that have created this Brugada polygenic risk score that Elijah and the group did the combined. If you have this plus this Brugada mutation in sodium channel plus your risk score, it makes you look like this. Do you think that discovery is something that is on the horizon for genetic test companies to add to the Brugada test, such that if you and I order the test because we think our patient or the family has Brugada syndrome, they'll not only tell us the SCN5A mutation status, but they'll also give us, and the polygenic risk score, the PRS is X. Do you think that's 3 months away, a year away, 3 years away? What would you guess on what needs to happen yet before our patients may start to learn that their risk score is X, Y, or Z?
Yeah, that's a incredibly important question, and something that we take a lot of time, as I'm sure you do, Mike, and everybody else in this field, to really kind of try to go through this with families, because it's really important. What you're talking about is the promise of precision medicine. So someday, utilizing the whole genome to be able to predict disease, predict how it might manifest in somebody, how severe it might be. And this is one example of how just a handful of variants, 4 of them, might predict how a disease may manifest on an ECG. But it's certainly a complex issue. In our last paper that we discussed, what is it about that KCN-H2 variant that made lumacaftor sort of irrelevant in that situation? Well, I don't know. What is it in those cardiac myocytes that was expressed differently in that patient? All those other things that might go into this. So while the dream of precision medicine is certainly there, we can see it, we know how to get there, I think we are probably still a little ways away from being able to clinically use it, to clinically make it something that we feel comfortable going to our families with and saying, I'm going to stand behind this because it's a quickly evolving field.
Mhm.
So I think certainly the SCN5A positivity is important. I think that's well established. I think how other variants may play into that, either from I don't have an SCN5A, but I have Brugada perspective, or I do have SCN5A, but I may or may not show Brugada. I think we're probably still a ways away from being able to incorporate those more complex genotypes into how we counsel families because of all those things we still have to discover.
And I think that's interesting for our SADS families to be reminded of is here we have a great paper, a great finding published in a really, really great journal that doesn't necessarily mean that it's going to be clinically available tomorrow. And that these advances and the translations, some of them never translate or materialize to actually really, really mattering for the patients that Andrew and I take care of, that we take care of, while others are immediately implementable and they're going to start changing practice tomorrow. So that one's an exciting discovery, but it's a stay tuned one in terms of when and if it will help Andrew and me be better physicians, doing a better job, taking better care of these incredible families. Well, this is a perfect setup from Toby in Austria. So hello, Toby. Anything happening in the CPVT world? So might you, Andrew, have an RYR2 or a CPVT paper that you could give us?
Well, unfortunately, this year in Circulation, Genomic and Precision Medicine, they were without a full study on that particular topic, most unfortunately. But there is absolutely some really incredible CPVT research going on. I do have one that may qualify more broadly for CPVT patients and for sort of arrhythmic cardiomyopathy patients. This one is from Deborah Cragen, out of the College of Medicine in South Florida, University of Southern Florida. And this is really an interesting paper about how genetic and genomic counselors and genetic cardiologists and regular cardiologists have some variability in how we might discuss genetic findings. And so the title of this paper is Evaluation of Clinical Practices Related to Variants of Uncertain Significance in inherited cardiac arrhythmia and inherited cardiomyopathy genes. And so what they did is they targeted about 100 practitioners, some of whom were non-cardiac genetic counselors, some of whom were cardiac specialized genetic counselors, some of whom were cardiologists. And they said, here's a case. And that case is basically of a kind of an unclear clinical picture. It's a young woman who had some fainting episodes when she exercised as a young and as an adolescent, as a young woman, but has been asymptomatic ever since. And she comes in with a variant of uncertain significance in a gene PKP2, which, as you know, and it can be associated in some situations with arrhythmic right ventricular cardiomyopathy. And it was really sort of an incidental finding. There was perhaps a unexplained sudden death in the family, but it was really unclear. And it was meant to be an unclear clinical vignette. What was clear was that in this particular vignette, the entire evaluation was negative. Echo, MRI, everything. Yet you have this variant of uncertain significance in PKP2. And so the question was, presuming that this is a VUS, so there are definitely ways to clarify a VUS, but for the sake of argument, say this is a VUS in PKP2 with this clean bill of health, with this family history, what would you do? And they asked these providers about, what would you do in these types of situations? And there was a lot of heterogeneity, as you might expect. So I'll just give you a couple of examples. So one of them said, one of the questions was, would you start this individual with a negative clinical evaluation and a VUS in PKP2 on a beta blocker? 6% or so of cardiac specific or cardiac specializing genetic counselors said, I might. 33% of genetic counselors overall said I might, and 44% of cardiologists said I would start this person on the beta blocker. Would you limit this individual's exercise, which sometimes can be needed in patients with ARVC? Again, with a clean bill of health and the VUS on genetic testing. 0 of the cardiac specialized GCs said I would limit this individual. 29% of the non-cardiac genetic counselors said they would, and 34% of cardiologists said they would. And I'll share one more with you. They asked, would you expand this genetic test to others in the family to identify individuals who might be quote unquote at risk of disease? 7% of the cardiac specialized GCs said they would. 33% of genetic counselors overall said they would. And the remarkable 60% of cardiologists said they would. And so I think big picture, it does show that there is tremendous heterogeneity in how clinicians of all different backgrounds pursue variants of uncertain significance, and probably highlights the need to kind of unify our thinking as an overall profession. But I found this paper to be very illustrative for those reasons.
Yeah, and I think we'll close on that one, because that one we could talk for a long time on that. Wouldn't you say, Andrew? I mean, I think the whole, and our families are well aware of the VUS issue. Many of them will say, hey, I have a VUS. They know that those letters, they know it stands for variants of uncertain significance. And you used a nice word, heterogeneity, as opposed to perhaps the maybe sobering reality, which is we have a bit of a mess going on out there right now, don't you think, where we are so Wild West in how we're navigating the VUS issue, as you illustrated. This is a great article, but how it points out, and it's a bit sobering to me and disappointing, that we don't know how to act on these. We don't have a systematic way of knowing whether we can upgrade or downgrade. We don't know that sometimes you and I are upgrading a VUS in a split second just by the report and the patient, because you and I, after all, are the ones who take care of the patient. We know why we ordered, who we ordered it on. And this scenario that you gave is truly one where you should be very, very careful to act on that PKP2 VUS. But there are others, to tie it into Toby, for example, where RYR2, the CPVT families, they know that they're plagued with the vast majority of genetic test reports for their RYR2 variant being called a VUS. And yet you and I can see that family where we knew that patient had CPVT. The genetic test company called it a VUS, and you and I, in a split second, said that's not a VUS. They might have had to say that, but you say, as the genetic cardiologist, that is that patient's CPVT1 caused a mutation with a lot of confidence. And so don't you think that our whole VUS heterogeneity that's going on out there is a bit of a VUS quagmire that we definitely need to do a better job of in 2021?
Yeah, I agree fully. I think it's, anytime science rapidly advances, I think it behooves all of us to come together to make sure that the way that it is applied to families and to patients is uniform, and that we're thinking similarly.
Yeah, and before we let you go, I've got two things for you. You're going to say anything you want to the SADS family community, and also grab your smartphone and show me a picture of Carter. So what you don't know out there is his oldest son is a teenager. And when Andrew was in my lab, Carter was born. And so I have a picture of Carter in my mind as baby Carter. And so I want him to show me and the world teenage Carter. So you tell your final words, you find me a picture of Carter, and out there, everybody, that's a trade so that I can show you the latest picture of my granddaughter. So you go first.
Okay, happily. So first off, thank you, everybody. This was an absolute pleasure. You know, I think the first thing is thank you for trusting us with the care of your children and the care of your families. You all have been through something that's really terrible, and you're coming at it from a place that I as a father can only imagine what that's like. So thank you for trusting us in the care of you and your families. You know, we do this science, we read these papers so that we can stay up to date. That's the best way to secure that trust and take care of your family. So thank you. And speaking of which, if you can see it, let's see.
Perfect.
So that's Carter and Sawyer Christmas morning. Carter was small enough you could hold him in one hand during our graduate school work. So it's been great.
And not to leave his younger son unnamed, that was Sawyer. And Andrew, thanks for joining us. And those of you on SADS Facebook Live land, you know, be sure to come back next week, episode 48. You're going to meet the Wizard of Oz. That's Erin, the behind the scenes who's making all of this happen for us, and what her role is on the staff of SADS. You're going to meet Marcia and her role in education for our foundation, and Jan, her role in development. You could donate even now and make her day. SADS.org, top right corner, donate now. You're welcome, Jan. And you'll meet our CEO, Alice Laura, next week. And they're going to share who they are, and more importantly, what are they doing for 2021? What's their vision? What's their passion? What do they want to do better? What do we want to do better as an organization on behalf of you, the amazing families out there? And so here, that is last week's picture of my Jaden and her mother, my daughter-in-law. And Jaden, her birthday is in 6 days. And guess what, everybody? I'm leaving after we hang up right now to head over there to celebrate her birthday tomorrow. We're doing it early because her dad, my son, is on call next week. So we're doing her birthday party tomorrow. And so great to get to be with you all. Andrew, best to you, best to your family and career. And can I invite you to come back soon to talk about the questions you and your team are asking, and then do another in 6 months or so. Great papers coming out in the journal world that our families might want to know about.
I'd love that.
That'd be great to have you. We'll do that as a rain check. And so everybody out there, stay well, stay safe, stay corona-free for as long as you can. And let's stick with this together. And we all together will live and thrive despite your diagnosis. Take care, everyone.